Talk.
We'll talk. Okay, so I want to talk about the decomposition theorem, studying the decomposition theorem over the integers. And yeah, so much of this will be quasi-known to some percentage of the audience. So we want to start with x in P. In some Pn, a projective variety. So if x is smooth, then we have many important and useful theorems. For example, the cohomology of x with integral coefficients satisfies a kind of derived Poincare duality. The rational cohomology of x satisfies hard Lefschetz. And then we have pure Hodge structures. We have the Hodge-Riemann bilinear relations. So, I mean, if you don't think about these every day, these are just some prediction of the signatures of certain forms that you can cook out of the cohomology of x. So, for example, if you would like to know the signature on the middle, on the middle cohomology of this, then it tells you the signature in terms of the Hodge numbers of x. Okay, so if x is singular, so all of these, all statements on the left for the cohomology of x fail. But instead, we can consider the intersection homology of x. Should do Goreskian McPherson. And then we have Poincare duality holds, and we have hard Lefschetz and pure Hodge structure. And relations. And the proofs for intersection homology or intersection cohomology are much, much harder, but they are now known theorems. But there's this, so in the first paper of Goreski and McPherson, in their first paper they noticed that derived Poincare duality does not hold. So an example that will be important in this talk, so I'll keep it over here. So if we consider C inside x tilde and 8, so this is a projective smooth surface. And I guess I want to assume also that the integral h2 of x is free. Then we can, and see this should be an ADE curve configuration. So you can take as X tilde a smooth compactification of some.
You can take it to be P2, right?
Sorry?
You can take it to be just P2.
Why?
Oh, it's AD surface. You mean with all the sections?
Yes, exactly. And I wanted to consider this contraction map. So, map contracting C to a point. Okay, so there's this lovely theorem of Rauert that tells you that if you have a configuration of curves on a surface, you can contract them precisely when the intersection form of this curve configuration is negative definite. And that's this AD curve configuration satisfies that condition. And we have that the determinant of the Poincaré form on H2 of X is something like determinant of the Cartan matrix. And so this implies that there's an example that shows the failure of Poincaré duality over the integers for intersection cohomology. And a very similar example was pointed out in this final little remark in the end of Gressy McPherson's paper.
Intersection. It's the same.
It is the same in this case. Correct. Is there another question? And so this seems like an extremely difficult question to decide when this holds. And we can consider the following local variant. Of this question, which is for which determine the P torsion in the stalks and co-stalks of ICZ. Integral
For instance, if there's no torsion in the stalk and stalks, that's implied that.
Yep. So that's a remark that no P torsion. So whenever I say P torsion, I always mean in stalks or co-stalks. It's very important. So, this implies that the integral of IC. This implies that if I invert P, so this is the P at X, then this satisfies Poincaré duality, but not conversely. I think. I mean, there's probably not conversely.
That's correct. You have no P torsion in stalks, now you have no P torsion in co-stalks. Is that right?
That's false.
Or a C sheaf.
Yeah, completely false. Completely false. The point is that the IC sheaf is not self-dual.
It's not self-dual.
Yes. And that's very often you see this situation where, for example, on the Afan-Grassmannian, all the IC sheaves essentially have no p-torsion after this Merkovich-Villornen conjecture that was solved by Acha and Ryder. There's no p-torsion in the standard sheaves or the IC sheaves on the Affine-Grassmannian, essentially, like in type A, no torsion. But in the co-stalks, this is extremely complicated.
And then stupid question, what is the IC sheaf and how is it defined? Is it just
Yeah, so the ICXZ satisfies. So I'll probably get this wrong, but so we choose a stratification. So stratification. And we consider that I lambda the inclusion of x lambda into x. So it satisfies I lambda upper star is in D strictly less than minus dimension of x lambda.
I think that still there is a unique thing which satisfies this.
Yeah, but there's a subtlety that in the in the co-stalks, this should be torsion. So if we take H, the cohomology sheaf of this guy, this should be torsion for J equals minus the dimension of x lambda and vanish below. So there's an asymmetry. So like if you think about just a point, so the abelian category of Z modules inside the derived category of Z modules is just things with cohomology concentrated in this degree. But if you take its dual, the torsion part shifts into degree 1. And so you have two different T structures and you glue them. So there's IC and then there's ICXZ and there's IC plus XZ. And these are exchanged by duality, depending on which T. Okay, so modulo.
But it's saying that there's a unique
Extension of the constant Schubert space.
Exactly. And also once you interchange the two T structures. So just a nice exercise. To get used to these things is if you take the quadratic xy equals z squared inside C3. So the constant sheaf if we consider the constant sheaf shifted by 2, this satisfies I 0 upper shriek of f is something like in degree 0, 1, 2, z1, 2, z0. Exactly, yeah. And that so the IC of this x over the q has no self-dual Z form. Okay. So there's really no way you can extend the intersection cohomology complex to satisfy Poincare duality in a kind of naive sense. And the kind of minimal self-dual extension is the direct image, so which we would call a parity sheaf, is the parity sheaf. F is the resolution. Okay, so the kind of, if you want to extend the constant sheaf on the open part over 0 in a kind of reasonable self-dual way, that you're kind of forced to take the parity sheaf. Okay. And just one more remark that you already see in this example. If X has isolated singularities, the question of P torsion is equivalent to understanding P torsion in the links to each, in the integral cohomology of the links. So this is probably a very hard problem in general. So, so for example, as a link, I can have the cone over any, like an S1 bundle over any projective variety. So in some sense, I can just get arbitrarily complicated torsion. And if I just give you a manifold and say, what's the torsion in its cohomology? This is probably hard. So we can expect this to be a difficult question, is what I'm trying to say. And so in this example, here the link is S3 mod mu2. It's RP3, which has 2 torsion in its cohomology, which is precisely where that is coming from. Okay, so as with all of these questions, we would like to study it via resolutions, and I want to explain in some kind of, to some rough approximation, what the proof of Cataldo and Migliorini gives us for these questions. And it's not particularly, so their work uses Hodge theory and these kind of things in a very non-trivial way, and their work is, I think, extremely beautiful and quite deep, but somehow what you can get out of it for integral cohomology is much less deep, and so I can explain that reasonably quickly.
Question of torsion, torsion of plus stock, while the torsion of stock is easier.
No, because so if you take the so just imagine you have an isolated singularity and you have a constant sheaf, and you want to extend it across using the Deligne construction. Then you see kind of in the IC sheaf, you see essentially up to the middle dimension in the as the cohomology of the link. And in the co-stalk, you see the rest. And so putting the stalk and co-stalk together, you see everything.
Which is actually proof of this remark in one direction here. But somehow it looks like, so somehow it looks like, so you're saying that you can see the cohomology of the link through the stalk and the co-stalk, but somehow it's not obvious that the converse statement is true. I mean, you basically just explained that if there is p-torsion in the cohomology of the link, then there is p-torsion in either the stalk or the costalk.
Yes.
Somehow he used only half of the stalk and half of the costalk, so somehow it's not kind of.
No, I used all of the stalk. All of the stalk of the IC gave me half of the cohomology, like up to.
Okay, sorry.
And then the co-stalk gave me the other rest.
Okay, sorry.
Okay, so I want to explain how one looks at this question. So you consider x tilde to x a resolution of singularities. And for DCM, for Cataldo and Migliorini, which I'll explain kind of in passing the whole time, we should assume f is projective and x tilde is projective. But this will kind of be relatively unimportant for the question of when does the decomposition theorem hold for this map, but it's actually, if you want to follow the Cataldo and Migliorini proof, then one needs these additional assumptions. And generally in order to get the general case, you'll compactify your map or use Charles Lemma or something to reduce to this case. So we choose a stratification. And for all, so these x lambda connected, and this should be a finite stratification. And for each x lambda, choose a point. So we fix a point in each strata and a normal slice. A normal sickle slice. 2x lambda through. So we have the following all-important diagram. So this is a slice. And then we have so we get this Cartesian diagram. And the embedding of f lambda inside n lambda tilde equips the homology of f lambda with an intersection form the integers. And now a basic observation is that so I kind of want to simultaneously explain how you understand the situation over the integers, but also, but I also want to kind of explain in a few remarks how Cataldo and Migliorini go about proving it over the rationals. So just for this basic observation, assume that we know that we've already proven the decomposition theorem over the rationals. Then f lower star so this is the derived direct image of the constant sheaf with coefficients in Z. Splits as predicted by dt, as predicted by the decomposition theorem. So there's a little remark here that I'll make in a second, but so let's call this IF lambda. So intersection form associated to the lambda stratum. If and only if IF lambda has same graded rank. So let's say we take coefficients in some, okay. Just a field, a field. So if and only if when I tensor these intersections forms with K, they have the same rank as over Q. And basically, the way that one... So there's one remark that I would like to make about this, which is that this basic observation says nothing about the semi-simplicity of local systems occurring in direct image. So by that I mean that imagine that we have this statement that these have the same rank over K as over Q. Then this splits up into the intersection cohomology complexes of local systems as predicted by the decomposition theorem. So it's kind of combinatorial thing. But still we don't know whether these local systems are semi-simple or not.
So they actually over
Q, I mean, if you do this over Q, they can break up sort of further. I mean, you're not saying.
Yeah.
Okay, so as predicted by DT just means that there is a decomposition.
Into ICs of some local systems that may or may not be semi-simple. And then one needs to kind of find another reason for the local systems to be semi-simple.
And if you know it over various fields, then you know there is.
It should be. I mean, it's just a question about representations of fundamental groups.
No, if you know DT decomposition.
Ah, yes. Exactly. And you also know, so if you know the decomposition theorem, the decomposition over every field, then you know it over the integers. And it also tells you that then the ICs are pairing a self-dual. So IC is IC plus. Exactly. Every IC there is self-dual. So you can never get this IC as the sum end of a resolution. So in the semi-small case, so in the small case, there are no intersection except for the open stratum, and so everything is basically determined by what happens on the open stratum, and this is just a question in just group theory, like representation, modular representations of groups.
If some X has small resolution, then its IC will be self-dual.
Yeah, for example, Grassmannians, their ICs are always self-dual over the integers. in the semi-small case, there is only one intersection form, one piece of intersection form that can contribute for each stratum. And here the decomposition theorem is equivalent to each intersection form is non-degenerate. Yeah, so there's only the grading. So I didn't put the gradings in here because I'm lazy and I'll mess it up. But yeah, somehow you can only have one possible guy that can possibly be non-zero, and so the statement is that this should be non-degenerate. And DCM prove this case by embedding. So if we imagine, so we have, let's so assume x lambda is a point stratum. So in that case, n lambda is just, we can just take n lambda to be x, n lambda tilde to be x tilde, and semi-small implies that the dimension of f lambda is half, well, is less than or equal to half dimension of x tilde, and assume equality. Then what DCM show is that the if we consider the this is our intersection form, and they embed this into the, so this is by some class map. So this is an intersection form on the top components with respect to how f lambda sits inside inside x tilde. And so if you want to understand this intersection form, so basically if you define this intersection form, you kind of take your classes inside x tilde and you move them so that they're transverse and then count as intersection points, but you can also do that inside x tilde. And so that gives this isometry. And then, so basically you want to say that for some reason, the image of this restricts to an... so on this whole space, the Poincaré form is non-degenerate because this is a smooth space. But you would like to say that the intersection form restricts to the image of this to give something non-degenerate. And then they use Hodge theory to do that. So
Non-degenerate on top of all.
exactly. Just this particular one.
We said.
I mean,
On the left one.
on the rest is zero.
Yeah.
Is non-degenerate on, yeah.
You can prove it in all characteristics.
No.
Yes, so this is all Q.
Yeah, this is over Q. So this all works over the integers, but the next step doesn't. So DCM say the following, that HD of D of f lambda maps into So the Hodge class is inside here, intersected with the primitive classes for X. And then
Just come from the last line.
from X.
From.
So there's this. So if you think about these classes, so I just rubbed off the surface case, but so you have some ADE configuration mapping down to here. And now any ample line bundle on X tilde, there's no way that these guys will be primitive for any ample line bundle on X tilde because they're whatever they're called, effective, or they're subvarieties, so they intersect any hyperplane class non-trivial. But the kind of miracle is that if you pull back an ample line bundle from X, then if you think about a hyperplane section of X, it looks something like this, like it'll miss this point. And so it doesn't intersect any of these classes. And so it actually goes into these primitive classes here. And then...
What do you mean by primitive class for
a non... I just mean in the kernel of...
I mean, it's just Gilbert multiplication by this.
Yeah. And then the kind of miracle is that pullbacks of ample classes under semi-small maps satisfy hard Lefschetz and Hodge, which they prove by an ingenious argument. So basically you've got this thing where you'd like to know it's non-degenerate, and it embeds inside something which by the Hodge-Riemann relations is definite, and so you restrict it to something definite that stays definite. But notice you lose control of the characteristics here. So in order to pull this argument off over characteristic P, there's two issues you need to deal with. Firstly, the fact that this statement will fail, so you need somehow to control when does something that satisfies hard Lefschetz in characteristic 0 satisfy hard Lefschetz in characteristic P. And even if you've solved that issue, you've got some space with a non-degenerate form on it, and you're restricting to a subspace. Kind of anything can happen. Okay, so.
It's strange because somehow the equation theorem is a local statement, and here you kind of looks like you're heavily using the fact that your axis projected.
And this is the same question you asked when I gave this talk last time in Kyoto. And this is a very funny thing. So this is a philosophically kind of interesting point that Sasha is raising. So is constantly raising. He's kind of, but I think it's a very valid. It's a kind of extremely interesting point that in this whole story, somehow what Cataldo and Migliorini are very good at doing is reducing some local statement to some kind of global statement about. So you want to know some splitting at some point in X, and you reduce it to some question about the global cohomology of X tilde. Right? And yeah, it seems somehow, on the one hand it seems kind of possibly philosophically wrong, but on the other hand it's kind of spectacularly successful. So. So that was the case, the semi-small case. And now, in general, the kind of predicting the radical of the cohomology. So you still have this intersection form. And predicting the radical, so they essentially use the reverse filtration to predict the radical of this thing. And they discover a kind of miraculous compatibility between the perverse filtration and various Lefschetz operators. But this is much too complicated to go into now. And just one remark. So in the semi-small case, so before, this, the fact that these guys have the correct rank is, what do I want to say? Yeah, so there's two parts of the decomposition theorem, namely, does the thing split into a direct sum of intersection cohomology complexes? And this you can deal with by taking normal slices. And then there's the question of, does the direct image, are each of the local systems involved semi-simple? And this you can't deal with by taking a normal slice. So in the semi-small case, the relevant local systems so you have pi1 of the strata, and this acts on the, so the local system involved in the decomposition theorem is the permutation action on the top dimensional components of the fiber. And so it factors over the permutations on the top dimensional components. Of fiber F lambda. And hence is semi-simple. Okay. So in the semi-small case, the local systems you always get factor through some finite group, and hence a semi-simple in characteristic 0 by finite group representation theory, Maschke's theorem. And the question in general so they use Deline's theorem. Okay, so this is another point where you lose, massively lose control in characteristic P. Okay, so here you can hope to estimate what's going on, whereas here, I think it's very difficult. Okay. So now I want to discuss Schubert varieties. So are there any questions? Sorry about that. And I should say that throughout this, the proof, the use of the weak Lefschetz theorem and hyperplane sections occurs the entire time. And so this is also kind of disastrous in representation theory because taking hyperplane sections in something that you know generally takes you away from something that you know. And and Migliorini was telling me that kind of every time he took a hyperplane section, it kind of hurt him.
So, I just want to ask a comment about this perverse filtration. So, is it computable in some sense?
So there's a beautiful observation in. So a lot of the stuff is kind of obvious if you. But there's a. So this is the cohomology of the resolution, and so it carries a perverse filtration. So we have this map down to X, and the direct image carries a perverse filtration, and so does this. But you can just give a purely linear algebraic characterization of this perverse filtration. So the perverse filtration is equal to the weight filtration action of So imagine that you just apply the decomposition theorem to the constant sheaf here. So this breaks up into...
This is over Q or?
This is over Q. I mean, kind of... And this breaks up into ICs. And you know hard Lefschetz for each of the ICs that occur. And so you know that the filtration induced by the perverse filtration does satisfy this kind of property that successive subquotients satisfy hard Lefschetz with respect to shifts. And therefore, you can characterize the perverse filtration on this just using the operation of this operator. And that's, for example, that immediately shows that the perverse filtration is Hodge theoretic. Like that you get Hodge substructures and things like this, which is extremely important in the argument. So now the rest of the talk will be much more combinatorial, and I'll explain how to just apply this intersection form idea to give a new proof of this. Well, yeah. So basically there's a lot of torsion in the intersection cohomology of Schubert varieties. So Schubert varieties. So I want to take... given the corresponding Schubert variety. And so the theorem that I want to explain, basically how to prove, is that so the quantity which is defined to be the max overall X in N such that so this is just asking take every Schubert variety in this whole flag variety. I see. So grows as something like c to the n, where so basically it grows exponentially, and I think so. C is provably something like, I think, 1.09 or something. But, that's just silly. So remark, this is a new proof. I mean, I've talked about this proof before, but now it's finally written down, and I kind of understood some things a little bit better when I was writing down the proof. This is a new proof of an earlier result. Obtained using Zergel bimodule techniques. Partly joint with Schubert. So essentially, basically, I think that the Zergel bimodule techniques and diagrammatics for Zergel bimodules provide the best way of deciding if you're given a specific Schubert variety, what the torsion is. Like, so the first example of this torsion was discovered by Braden, and it's really, in any specific case, it's very difficult to do this calculation. So you have to understand the specific geometry of that specific case quite carefully. And any one example will probably take you a few pages to work out. Whereas these Zergel bimodule techniques kind of allow you just to, I have a computer program and I can plug it in and type torsion yes no, and it decides. But it gets quite slow. But you can check like for example, I managed to check an example in GL12 with these a reasonably complicated example in GL12. So it's reasonably effective. And so in order to prove this theorem, I used this formula that I discovered with Schubert, which basically expresses certain entries of intersection forms in terms of the nil-Hecker algebra. So it's much simpler than the diagrams. And I guess what I'm explaining today is, in some sense, trying to explain where this algebraic formula comes from. And so this has many applications. To representation theory, which was the motivation. So A is the expected. So what people expected to be true for Lustig's character formula. Which I talked about last week. So Lustig's character formula is a formula for simple modules for reductive algebraic groups in terms of affine Cauchy-Lustig polynomials. And this would imply that, so this is by work of Zergel, this would imply that Tn is grows linearly in n.
What is Tn?
Mn. And B, this James conjecture, which was a conjecture on simple FPSN modules. So basically, the conjecture was that you can reduce a module for Sn over the complex numbers to characteristic P. You can factor it as first going through a Hecker algebra at a root of unity. And that question of going to a Hecker algebra at a root of unity in characteristic 0 was solved, and then the conjecture was that under reasonable bounds on P and N, this should be, the second stage should be trivial. And that implies by an observation of Zhou Chuang that Mn grows quadratically. In N. So I want to explain a very simple formula for Bott-Samuelson resolutions, which I think is kind of nice, but I'm sure it's in some sense already known. So if we fix an expression, so we denote by PS containing B a minimal parabolic. And then we can consider this Bott-Samuelson variety, which is just so I'll write it this way. So the first copy of B acts by B inverse B, etc. So I want to write it like this for reasons that'll be clear in a second. And you have this T action. So this is, as a variety, this is very simple. It's just an iterated P1 bundle over. So you take a P1 bundle on P1 and then take another P1 bundle on that and continue. That's what this looks like. But the multiplication map to the flag variety provides resolution of singularities, etc. So we have this, we consider the torus action of the Bott-Samuelson, and the fixed points are in bijection with the sub-expressions. So that means E is a sequence E1, EM, where each EI is in 0, 1. And something on this side corresponds to the fixed point S1 to the E1. So call the class F in the T-equivariant cohomology of the Bott-Samuelson combinatorial if there exists F1 up to Fm in the T-equivariant cohomology of a point such that Fe, so this is the localization, has the following form. So it's determined by these polynomials in a very simple way. So these classes are, I think that they span the homology over the rationals, but probably I think they don't span over the, well, I'm not sure. I think they don't span over the integers. And now there's this funny little lemma, which, so this is the kind of, some kind of geometric explanation of this formula with Schubert, which you call the Euler class lemma. So an example of a combinatorial class is that if we take V a B to the M module, and we take L of V, the corresponding vector bundle, then the Euler class of this guy LV is combinatorial with Fi being the kind of the determinant of the restriction from B to the M to B of V, where this B is the ith copy. So if we have a BM module, then we have a whole lot of, we can look at its characters on each one of these BIs. And then the statement is that if we take the product of these characters, then we get the Euler class of this this vector bundle. And then we have this Euler class lemma, which says that P lower star of a F combinatorial, P lower shriek, is P is the map from the Botz-Hamilton down to a point. It's just given by some simple de Maizière operator, so S1.
In addition to supplementary class, so you're acting by SI on the classes?
Yeah, so I have these F1, F2 up to Fn, and then I say that its localization at one of these fixed points is given by this product.
Well, only SI to the power EI?
SI, like this is, EI is 0 or 1, and so this is either 1 or SI. Either act or I don't act. But somehow, so expressions of this form were what showed up in these examples. And basically, so how much time do I have? So I have another 25 minutes, great. So somehow, from mucking around with Zogel bimodules and things like this, the expressions of this form show up a lot. And somehow, this is some attempted explanation. So now I want to explain what... So basically, the idea is that... I'll give the rough idea first, and then I'll give the explicit construction.
Idea of what?
Yeah, that's what I'm saying now. I want to tell you the idea. So to produce these... So it seems very random what stays on the board and what doesn't. So the idea is that we fix such an expression. And I want my f's to be very special, so I want to take Sn inside some big Sn, so n acting on a polynomial ring in Xn. And you should think that this is small, e.g. n equals 4 or 5, and this is kind of arbitrarily large. Okay, so you can take n equals 100 or n equals 200 or something. And this will just be the kind of playground, and everything will happen here. And so you fix an expression of the following form. Alpha m to the a1, ds2, alpha m to the a2, dsm, alpha n. Same alpha n all the time, which is very important. And alpha n is xn. Okay, so it's precisely the root that's kind of on the border of this guy. So that's step one. We fix such an expression, and we assume that C is in Z, and C is non-zero. And if you experiment, you can see that it's very easy to get, in some sense, arbitrary numbers C in this way. I mean, you can very easily get any number you want, but also they grow very quickly. For example, you can get some Fibonacci numbers, for example.
I mean, in principle, it's polynomial, isn't it? But
Exactly.
yeah.
So this is just some stupid condition on the degrees. And two, we will construct a Schubert variety XX inside, so we'll call it XW, inside GL big N mod B, and a resolution and a Bott-Samuelson resolution, which will be, so I wanted to denote these by xy, xm, and fix reduced expressions xi, reduced expressions xi. And so now we will construct an extremely so note that this expression here, this will be some very long element of S4, so there's no way that this will be a reduced expression. Whoops. Sorry. So this is the resolution. So W I haven't specified yet what it will be. But now kind of comes the punchline, which is that let Wi be the longest element in this little Sn. So we have this Schubert variety here, we have this Bott-Samuelson resolution here, and we have our point xi. And then we have this normal slice. And then we have this fiber. And then the kind of punchline is that F is isomorphic to a much smaller Bott-Samuelson variety. So this is the Bott-Samuelson resolution for a highly non-reduced expression. And the second thing is that the Euler class, so the second point is that this fxi inside this normal slice is half-dimensional. And then the third point is that the Euler class of this normal bundle to is combinatorial. And this implies that the self-intersection of this fiber is C. So that's the whole point. So somehow, starting with an essentially quite arbitrary number, one can produce a resolution which has this miraculous property that's kind of semi-small at this point, and that the fiber is irreducible. And it's
I mean, if your expression non-reduced, it's not.
so there's two Bott-Samuelsons here. There's this guy, which is reduced, and then the fiber is miraculously also a Bott-Samuelson resolution.
All by itself.
Yeah.
No,
For a very non-reduced expression. And that's not, like, for example, if you look at Braden's examples, it's not so ridiculous that this happens, but it certainly doesn't happen always.
Sorry, just the limitation. So xi are coordinates, and then there's a reduced expression for x.
Ah, sorry.
And,
I mean, these are big x's.
oh, okay.
These are big x's and these are small x's.
No, I don't think you want to call them bigger because you always, I mean, you Schubert varieties have
Yeah. So just
sized axes.
to.
Sorry. And now, who are these x's which are in the while loop?
So this is very important. I forgot to say that the xi's are in Sn.
Some elements.
Some elements. And you just have to believe me that you can kind of very easily get very interesting numbers in this way.
So, but in this formula for C, you have probably DCI. Right? So the formula you just pointed. Formula 1.
No. So these guys, this is a de Maizière operator.
Oh, okay. Corresponding to
Corresponding to an element in the Sn. And I just realized that I failed to say that these are de Maizière operators, but these are divided difference operators.
Can you say that?
So x's are reflections, or?
No, these are just elements of algorithm. I mean, of course, you can just take them to be reflections if you want by adding a lot of zeros. But the principle of this thing is that there's something happening in a small, I don't know. I like to think about this as some kind of dynamical system on the finite, on a small flag variety. Namely, I look at the cohomology ring of this small guy, and I have inside this Schubert classes, and I have this operator of this kind of raising operator alpha n that allows me to go up, and then these de Maizière operators that allow me to go down. And so I go up, and then I go down, up, down, up, down, up, down, up, down, down, and keep going, and I see what I get, and then I go down, and I get a number, and I can get very interesting numbers in this way. And then somehow one can rig the situation to put these numbers, to actually realize these numbers as some self-intersection of a fiber inside a much larger box.
So is this thing that you can do it for any xi such that c's and z, you can find
Exactly.
what's written on the middle word?
Yeah. And it's like in the last 10 minutes, it's completely explicit and might be interesting for people that like explicit reduced expressions.
So that only that appears there is IWI.
This is... Oh my God, this is a disaster. I'm sorry. I think
You can find a W so that this diagram occurs.
yes.
And so that
And in some sense, this expression just naturally arises. What I was unable to show is that this normal bundle is actually a vector bundle of this form. But it's much easier to show that its class is combinatorial, and therefore one has this lemma that gives itself a this.
you mean it's not coming in and obviously from this Baroque construction.
Exactly. Yeah. I tried for about a day to see if this was really of this form, and I cannot decide whether it's of this form or not. It looks like it. I don't know. If I had to guess, I'd say it should be, but who knows? So basically, all I need to tell you is how to construct W. So one does the following thing. So I'll just draw a picture of W as a kind of string diagram. So this might be n equals 5. And then I have something. This is the big end. Okay. So now we start off by putting the longest element. So I'll draw boxes. Sorry? Ah, sorry. Let's say n equals 4. And so now I have this first, so basically my numbers, so here I'll have some number which will be an, am. And the idea is that, so let's say that this is 2, then I do. And then comes my first xm. And then maybe am is 2 again. And then maybe am is 2 again. Etc. Okay, so the idea is that, so this is an extremely non-reduced expression, this guy here. So if I delete these other strands, this cancels enormously. But somehow one can just kind of keep adding strands to make this reduced. And yeah, so this will be, this is a picture of what W looks like.
The difference between big and that's the sum of the AIs.
Exactly, yeah. N is larger than n plus some of the AIs. So you can kind of only put this example in some GLN, which is kind of bounded below by the number of AIs that occur. But I find this kind of, it's a very kind of efficient way of producing an extremely singular point in a Schubert variety that nonetheless has this remarkable fact that the fiber is just completely comprehensible. And so it's possible that that has other applications. And also, I remember Hiraku asked me a question in Kyoto, which is, if you consider XX, so you have this open Schubert cell, and then you have this guy here, which is WI, and then you can ask what happens in between. And I kind of expected everything to be some kind of simple combinatorics to govern what happens in between. But I now think that that's not at all the case, that this kind of, in this middle area, you can have very, very complicated behavior, but somehow miraculously at this point you have a simple behavior. So that's it, I think. Thanks.
Questions? Can you maybe make one comment how this implies this exponential growth statement?
Yeah, so that's subtle. It's extremely subtle. So if you just, you could just program a computer and look what numbers you get in this way for some small values and for some, just bound something and just look what numbers you get. And it looks like the numbers grow very fast. But now you have to actually prove that you can generate, for example, can you generate primes that grow exponentially in the number of times you multiply by with an?
So, but I'm confused. I mean, eventually you're going to get torsion Schubert varieties which correspond to capital N, right?
Yes.
In this notation. So basically, the variety I want to fix is capital N, and then there's our other prime will grow will be capital N, and we want to show some exponential growth of these primes as a function of capital N.
Exactly. So one theorem you might like to show. So for example, you can show that Fn, so this is the n Fibonacci, occurs in something like, for n, in something like 4n plus 3. Cool. So you do this by encoding this matrix in this combinatorics, and so you can just iterate. You can iterate some operators and get powers of this matrix, and you get Fibonacci numbers. But now, it's an unsolved problem what prime divisors of Fibonacci numbers look like. Okay. So even though it's extremely likely that that, for example, you get primes of the form, golden ratio to the power of n, roughly of that order, that's not a theorem. And now I think that it's for us a moot point. There's lots of torsion. But for kind of number theorists, this is an extremely interesting question. And there's a theorem that the actual, so this is by Bourgain-Contourage. With some small additions, is that the prime entries in the semigroup, so grows exponentially in word length. So it's kind of remarkable that not only prime divisors, but actual entries that are prime grow exponentially in this semigroup. And so we can encode these matrices in this kind of combinatorics, and therefore you get the growth.
More questions? All right, so let's think through the